A harmonic polygon, okay, this blue thing here, in this case it's a hexagon, but n equals 6 without loss of generality, is one that is inscribed in a circle, okay, and is so here's the center of the circle, and is associated with a special point called the symmedian point K of that polygon, which has a very special property. If you drop perpendiculars from K onto the sides, the length of those perpendiculars are proportional to the side lengths. So Casey, in an 1888 book named The Sequel to Euclid, defines harmonic polygons as cyclic polygons with the special point K. Now recall that for a triangle, the symmedian point of a triangle has trilinears, which are essentially perpendicular distances to the sides, which are precisely the side lengths. So the trilinears of x6 are A, B, and C, the side lengths. So you can generalize this to polygons, which is what we're doing now. And you can say, okay, a harmonic polygon is one that is inscribed in a circle and is associated with a point K, which has this property of perpendiculars being proportional to the side lengths. Okay, now there's another object that you can immediately construct, and it has its counterpart in the triangle as well, known as the Brocard circle. It's this brown circle here. And when you can simply draw a circle with a diameter, with one of its diameters being KO. So it's a unique circle, which has KO as a diameter. Okay, the center of the Brocard circle is shown here as this brown dot, and I'm labeling it O subscript BR. Okay, now Casey in 1888 also says that if you fix K and you fix O, okay, there's going to be a porism, like a Poncelet porism. And Poncelet was had written about porisms back in 1822, and this is an 1888 result, right? So it's 40 plus years later. 40 or 60 plus years later, right? But what we're seeing here is the following. If you fix K and O, there's a whole family. There's a one-dimensional family of harmonic polygons which keep K and O fixed and the circumcircle fixed, and this family is going to envelop a Poncelet caustic, which is shown here green. And this is sometimes known as the Brocard inellipse because its foci, omega 1 and omega 2, are known as the Brocard points of this family. Now, if you recall what a Brocard point is for a triangle, there are two Brocard points in every triangle, right? There are these unique points in a triangle where you can actually rotate the sides by a special angle omega, known as a Brocard angle, and the rotated sides are going to all converge if you follow the vertices in counterclockwise order and you rotate the sides counterclockwise, they're going to converge in a first point omega 1, known as the first Brocard point. And then if you do it on the opposite direction and you rotate clockwise, they're going to concur at a second Brocard angle, a Brocard point known as, or sometimes labeled omega 2. Okay. Now it turns out that you get this generalization for harmonic polygons as well. You could rotate the sides by a fixed angle omega, and they would all concur on omega 1. And if you scan the sides in the opposite direction, rotate the sides in the opposite direction by the same angle omega, which is a fixed angle, you're going to concur at omega 2. So it just so happens that these two Brocard points are the foci of this generalized Brocard inellipse. Okay, so here's the Ponceletian family inscribed in a circle and enveloping this very special Brocard inellipse. The midpoint of the Brocard inellipse is the center, so the midpoint of the foci, shown here as O prime, is the center of the Brocard inellipse, and in general it does not coincide with the center of the Brocard circle OBR. So O prime does not in general coincide with OBR. In fact, I don't think it ever. No, there's a special setting where they do coincide, but that's not germane to this video. Okay, now the other object that I want to show you guys here are these two limiting points, L1 and L2, and they're limiting points of the linear pencil, in this case an elliptic pencil, defined by the circumcircle and the Brocard circle of this family. So you have two circles here, any two circles. In this case, they're non-intersecting. They're going to define a hyperbolic pencil. And let's show a few circles in this pencil. So here's a few circles in this pencil. And the two limiting points, L1 and L2, are shown here. Okay. it turns out that if you actually performed an inversion of the vertices of this blue polygon with respect to either limiting point, so let's do that. So here's an inversion. So here's my circle of inversion. So I actually have a generic. Let me go back here one step so I show you guys what I'm doing here. Here's a generic inversion circle, this red circle here, centered on point C. And here is a polygon whose vertices are inversions of the blue vertices with respect to this red circle here. Now it just turns out that there's a beautiful property of these harmonic polygons, which is if you perform these inversions with respect to either limiting point, L1 or L2, so let's place the center of inversion on L1, the inversive image is a regular polygon. So in this case here, it's a regular hexagon. My center of inversion is on that right-hand side limiting point of the pencil, this elliptic pencil defined by the circumcircle and the Brocard circle. And if I actually perform this inversion with respect to L2, let's place it on L2, I get a second regular pre-image of this family. So actually Casey, one way that he defines harmonic polygons, one alternate way, is he says a harmonic polygon is the inversive image of a rotating regular polygon family with respect to some point you pick on the plane. Okay, now if you go in the reverse direction, the pre-image is going to be the inversions with respect to either one of these limiting points defined by this beautiful elliptic pencil of circumcircle and Brocard circle. Okay, very well. So this is actually a good segue into the main topic of this video. I actually want to show you guys a couple of properties of what happens to this inversive image here of the harmonic polygon. Okay, so let's just recap what I precisely mean by that. I'm taking the vertices of this blue family, and I'm taking a particular inversion circle centered on C, and I'm drawing these red dots here, these inversive vertices at the inversions of the blue vertices with respect to the circle. Notice that I'm not actually inverting the sides, which would give rise to arcs, right? So the inversion of a line with respect to a circle is an arc of a circle, or it's a circle. Here I'm actually doing kind of a halfway inversion. I'm only inverting the vertices and not the edges of the original polygon. And then I'm finding out where these vertices fall after the inversion, and then I'm connecting them and saying, okay, here's a new inversive polygon. Now Casey talks about this in his book, and he says, okay, the inversive image of a harmonic polygon is also harmonic. So this family here is also going to be inscribed in a circle, and it's also going to circumscribe its own Brocard in ellipse. But that's not germane to what I want to show you guys here. What I want to talk about is what are isocurves for the position of C such that the Brocard angle of the inversive image is constant. Okay, so I'm showing here n equals 6. I'm showing the cotangent of the Brocard angle of the blue, the original family, and the cotangent of the red, cotangent of the Brocard angle of the red. So because it's a harmonic family, it's also going to be associated with its own Brocard angle, but they're different, right? And I'm using the cotangent here because the algebra is slightly simpler when you do cotangent. But it's a one-to-one map. Okay, so as I gyrate my porism here, you can see that the cotangent of the blues is 0.8706, the cotangent of the Brocard angle, and the cotangent of the red is 0.77. If I move my center of inversion, I get a different number, but it's still constant, right? Let's go over here. Okay, so what I want to do is the following. I can see here that if I just move my C arbitrarily, you can see there on the top that the cotangent of its Brocard angle is changing. So I want to ask the following question. What are the isocurves for C such that cotangent of the inversive Brocard angle does not change? And it turns out these are precisely, and this is a beautiful harmonious observation, they're precisely circles in the pencil of the circumcircle and Brocard circle of the original family. So here's a pencil. I'm going to go ahead now and place, for example, let me place my inversion circle, inversion center, in one of these circles in this discrete sampling of the pencil, right? The pencil is a continuous family. It foliates the plane. It sort of completely covers the plane, but I'm just showing here a small sampling of, let's see, 1, 2, 3, 4, 5, 6. And if you take the radical axis, okay, this vertical line here, also known as the Longman axis of this harmonic family, if you took this entire set starting in the limiting points, you have here 1, 2, 3, 4, 5, 6, 7, 8 circles on the left side, and then you have 7 circles on the right. Okay, so this is just a sampling. But the main result that I want to share with you guys is that if I actually slide C along any one of these circles in the pencil, the cotangent of my inversive Brocard remains constant. So let's do that. I'm going to slide C along a circle, as you can see here. And I'm tracking what that inversive polygon looks like. And I can show you guys that the cotangent of the Brocard angle of the inversive is actually constant. Let's move over to another circle. For example, this one over here. I moved over to this circle here, and I'm going to do the same sweeping. And you can see here that I've jumped to a different cotangent of my inversive Brocard angle, but it's constant. Let's jump over to this circle here, say this one over here, and let's now slide over it, still constant. Let's actually now move C to the right side of my circle family. So I'm over here, and I'm now scanning this circle, and you can see here that the cotangent of omega inv also remains constant. Let's move over to this other circle over here, and let's see if this is the case. Yes, it is the case. So a first really cool observation is the following. A given circle in the pencil defined by the circumcircle and Brocard circle of the original family, a given circle in that pencil, is an isocurve of Brocard circle, of Brocard angle of the inversive family. So this family, this pencil, is the family of isocurves. And this is quite cool. You could actually say, okay, let's see what happens if I slide along the radical axis, which is one of the circles in the pencil, right? So now I've placed C on the radical axis, and I'm going to slide it up and down. And you can see here that the cotangent of my inversive Brocard angle remains the same. But then you notice something new here. And that is the following, that if C is actually on this very special circle in the pencil called the radical axis or Longman axis, the actual Brocard angle of the inversive family remains equal to the Brocard angle of the original family. So this is observation 2. And that's quite cool. Now there's another area where this is the case. So let's now erase the circles, and I'm just going to move C along the radical axis. You can see here that it's 0.8706 and 0.8706. Now I'm going to make a jump. I'm going to make C jump to the Brocard circle. So instead of doing this, I'm going to do this manually. I'm over here. You can see here that as C moves closer and closer, well, when C is on the circumcircle, you get sort of a degenerate case, right? Because the inversion of the circle, of the circumcircle, is just going to be a straight line with respect to a circle centered on it. So this is not interesting. But as I move C closer and closer to the Brocard circle of the original family, I'm going to be approaching the cotangent of the Brocard angle of the original family. And in fact, if I'm on top of it, Brocard circle, if C is on the Brocard circle and slides over it, since the Brocard circle is on the pencil, I already know that I'm going to have constant inversive Brocard angle. But the other thing is that this Brocard angle is actually, again, equal to the one of the original family, 0.8706. So there are two loci for C for which the Brocard angle of the inversive is equal to the Brocard angle of the original family. And these are the Brocard circle, which is what you're seeing here, 0.8706, 0.8706, or the Longman axis. So it's the union of these two sets that gives me a family of polygons whose geometry is changing quite a bit, right? And it doesn't matter if I'm actually varying this in a Poncelet style traversal. That thing doesn't change, and I can place this inversion circle anywhere. I can place it over here, and I can place it on the Brocard axis as well, on Brocard circle as well. There you go. And I can make this guy move around And you can see that there's a non-trivial change in the geometry of the inversive images, but their Brocard angles are the same. Okay guys, so this is what I wanted to talk about in this video. Thanks for watching.